All right, so this chapter is about digital signals and switches. So we're going to be describing parameters of waveforms, different terminology. Among the terminology is frequency and period, and we'll go over how to convert between those two. And also what a periodic waveform is. We're also going to be sketching timing waveforms. We'll talk about serial and parallel transmission, manual switches, electromechanical relays, how diodes and transistors work, how the voltages, the output voltages in circuits containing these diodes or transistors that are being used as digital switches. We'll also do a little bit of I/O timing analysis in circuits containing relays or transistors, and then go over a little bit about how transistor circuits can be used as a digital inverter. So to start out, that graph at the bottom, that is the format that you will see over and over and over again throughout this course. This is how we represent digital signals and how they change over time. So on the bottom, the x-axis, there you have the time axis. Your y-axis is voltage, and we will be using, for the most part, the TTL voltages, 0 volts for representing a 0, plus 5 volts for representing a 1. And these kinds of waveforms are similar to what you'd see on an oscilloscope with the time related to the voltage. So when we use the term periodic waveforms, all we're saying is that it's a waveform that repeats, and each time it repeats, the pulses are all identical. So it's just the same signal repeated over and over again. Each periodic waveform has a period, and this is the time from one edge to the corresponding edge on the next cycle. So if we go back to this and pick out a point on this graph, we can, we could actually just start here on the 0, at time equals 0. Once we consider one cycle to be so this signal starts at 0, goes up to 1, and then here's the moment where it starts to repeat. It goes back down to 0 and goes up to 1 again. So this is one cycle, there to there. The time span for this signal is the period. So the total time that one signal takes, or one cycle takes. Frequency, on the other hand, is basically just the reciprocal of the waveform. Or you can think of it as, they show in that formula there, 1 divided by the period. And then for figuring out the period, the formula is just the opposite. It's 1 divided by the frequency. So this is how we convert between frequency and period. Period is measured in seconds or nanoseconds, microseconds, whatever. It's some time interval. Frequency is measured. It can be measured in any. It can have any unit attached to it that is anything per unit of time. So things like, I'm sure you've heard your internet connections as being described as megabits per second. Anything per second is the important thing. So anything per second can be considered a frequency. But if there is no unit, there's kind of just a general term called hertz. That's written as capital H, lowercase z. That can be used as a general term for frequency. Hertz just means per second. So here's some examples. If we're given a period of 2 microseconds, and we can find the frequency by just taking 1 divided by 2 microseconds, and that would give us 500 kilohertz. And you do want to be careful about tracking your micros and kilos and all the other prefixes so that your decimal places come out correct. But the other example there would be them providing a frequency of 4.17 megahertz. And then to find the period, you just do the same thing. 1 divided by the frequency, or 1 divided by 4.17 megahertz ends up being 240 nanoseconds. So here's our first example that we'll solve. They want us to sketch and label in that particular way of drawing out those diagrams where you have time on the x-axis, voltage on the y-axis. They want us to draw one of these diagrams representing a 56 kilobits per second. So they're giving us a frequency. Clock waveform. When they use the word clock waveform, typically the word clock describes a periodic signal that just alternates between 0 and 1, back and forth, continuously. So that's the kind of waveform we are going to be drawing. It's just 0 to 1 to 0 to 1 to 0, just this signal bouncing back and forth. And they're giving us the frequency here, and they want us to draw a diagram that describes this signal that we would see. And they also tell us that lows are going to be considered 0.2 volts and highs are going to be considered 4.5 volts. So, first what we want to do is find the period so that we can label the period appropriately on the diagram. So they give us a frequency. So to find the period, all we need to do is just take our equation, that Tp equals 1 over the frequency. And they gave us the frequency as 56 kilobits per second. So kilobits meaning 56,000 per second. So then if we go to our handy dandy calculator and we divide 1 by 56,000, we get a number that looks like that. 1.7, we'll round it to 1.79 times 10 to the negative 5th. Now, that is awfully close to times 10 to the negative 6, right? 10 to the negative 3 we know is milli. 10 to the negative 6 we know is micro. So if we know that, and we can see this number is very close, that exponent on that negative 5 exponent is very close to negative 6. What we can do to kind of shortcut so that we don't have to write out that very long decimal number, figure out, what 10 to the negative, that number times 10 to the negative 5 is, and then convert back to some other unit by then moving the decimal place back again. There's kind of this shortcut where it's 1 away from 6. And when you need to decrease that exponent, for example, negative 5 going to negative 6 to make it a nice even unit that we can use because negative 6 is micro, we need to shift the decimal place to the right by 1 so that the equivalent of 1.79 times 10 to the negative 5th, we move the decimal place over 1 so that we get 17.9 times 10 to the negative 6. So then we can easily say that that is in microseconds. If, let's say we had 1.23 times 10 to the negative, no, let's not make, let's make it positive. 10 to the 2. I'm just using low, simple numbers here just to illustrate the point, but we have this. We can see that it's close to 10 to the 3, which we know is kilo. What we can do then, if we want to increase we want to increase this exponent by 1. So increasing means we have to move this decimal place the opposite direction. While as before, when we had 10 to the negative 5, 10 to the negative 5, trying to convert that to 10 to the negative 6, technically that's decreasing because we're decreasing this negative 5 by 1, making it negative 6. Well, we want to increase this to a 3 so that we can make it a nice even kilo unit. So shifting the decimal place over 1 would give us 0.123 times 10 to the 3rd, which would be kilo. So that's a little shortcut you can do when you're doing some of these calculations. Otherwise, you could, I mean, it's totally fine to just, for the 1.79 times 10 to the negative 5 that we had, you can figure out what this is in just seconds, no prefix or anything, by shifting over 5 times, right? 1, 2, 3, 4, 5 to get 0.0000179, and then you can, so it would be that number of seconds, and then you can convert that into, by moving the decimal place, 1, 2, 3, 4, 5, 6, 17.9 microseconds. That's fine too. That shortcut that I use is more of, it's a shortcut, so it just makes things a little bit easier. But you do have to be careful about, you know, which direction you move the decimal place. If you decrease, you move it to the right. If you want to increase the exponent, you move it to the left. So anyway, we have this period now, 17.9 microseconds. So now we can make our graph like they wanted us to. They said it was a clock signal, or clock waveform, so it's basically going to be alternating like this, just alternating between 0 and 1. They wanted us to label, so they said that low is going to be 0.2 volts, so we'll just put 0.2 there. And they said high was going to be 4.5 volts, so we just put 4.5 there. And now we have to label, because we don't know how, you know, what time span this is working over. So you gotta, we'll pick out any particular cycle, and I'll just pick out this cycle here to indicate the period of the cycle, which we figured out was 17.9 microseconds. So there is our diagram. And that's what they show there. So then, just real quick, here's a little reference, because we've been talking about milli, micro, all this other stuff. This is just a table showing the common prefixes and what they mean. They're all in increments of powers of 10 to the 3. So 10 to the 3 to the 6, 9, 12. 10 to the negative, and the other direction, -3, -6, -9, -12, steps of 3 decimal places. So, and this just shows the prefixes and then their abbreviations as well. So they're asking, just as a few discussion points, what the vertical and horizontal scales of an oscilloscope represent. Well, it's the same as these diagrams that we've been drawing, right? So the vertical scale is your voltage, your horizontal scale is time. Then they ask what the period of a 75 megahertz waveform is. So we just reuse our period formula. Our period is going to be the inverse of the frequency, 1 over the frequency. They give us the frequency as 75 megahertz. So 75 with 6 zeros. 75 million hertz. And what does that equal? Well, let's go back to our calculator. And we'll just divide 1 by 75 million. One too many. 75 million. And gives us 1.3333. Repeating, times 10 to the negative 8. So 1.33 we'll round it to, times 10 to the negative 8. Well, like I said before, that negative 8's awfully close to negative 9, which would give us a nice even, if we go back to that table, what is 10 to the negative 9? It is nano. So we then can say we need to decrease this exponent by 1, so we can move this over 1 decimal place, and we get 13.3 times 10 to the negative 9, which is nanoseconds. So then the next question, last one, asking us about the frequency of a waveform with a period of 20 nanoseconds. So really it's just the same kind of calculation, but we're doing the opposite formula. Frequency equals 1 over the period. So they give us the period of 20 nanoseconds. So it's going to be 20. 20 nanoseconds means we'll have to take the decimal place that's here and go left 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. That many seconds. So then, going to the calculator again, we'll say 1 divided by 0 point, and there are 7 zeros, and then a 2 0, or just 2. Either way, that gives us 50 million. So this would give us 50 megahertz. And that will do it for this part of the chapter.